Hi everyone, welcome to our lesson on logarithmic functions and their graphs. So let's first start by defining what a logarithmic function is. So we talked about this a little bit in class today, but a logarithmic function is in the form f of x equals log base b of x. So b represents the base has to be positive, it has to be greater than 0, and it cannot equal 1. We're calling from what we talked about with exponential functions. And what you're taking the log of this x has to be greater than 0. It has to be positive, and we're going to use that to help us algebraically find the domain of logarithmic functions as we move through these notes. And from class today, you also might recall how to rewrite from exponential form to logarithmic form and vice versa. Y equals log base b of x is also equivalent to b to the y equals x. Okay, so let's take a look at how we can kind of relate these functions a little bit more. We talked about today how they are inverse functions of each other. So what that means is that if I have f of x equals 2 to the x, f inverse of x is equal to log base 2 of x. And recall that this notation of f raised to the negative 1 is just function notation for inverse function. If f of x equals 10 raised to the x, then its inverse is log base 10 of x. And notice that that is also the same as log x. We call this the common logarithm, and it has its own notation. When you don't see a subscript written in and you just see log x, you can assume it's base 10. And that is the logarithm that is used on your calculator, the log button. And lastly, if f of x equals e to the x, then its inverse is log base e of x, which mathematicians condense to ln of x, which they call the natural logarithm. So again, when you see ln of x, you can rewrite that as log base e of x to help you kind of evaluate or graph from there. So the common logarithm and the natural logarithm have their own notation of condensed forms. All of the other logarithms of other bases that aren't base 10 or base e will have a subscript there to indicate what base you're referring to. So kind of just to review a little bit more with inverse functions, you want to recall that they interchange the x and y coordinates of the original function, and that has to apply to the domain and range as well, since domain is x and range is y. So let's take a look at that on the next slide here. So if we know f of x equals 2 to the x and its inverse is log base 2 of x, then we can apply what we know about 2 to the x. We know these three ordered pairs. We know these three key points. Of course, there's more than three, but if we think back to when we did a lesson on exponential functions, we usually like 3 key points. And so using those, we can switch our x's and y's to obtain our new 3 key points for our logarithmic parent function. We also know that the horizontal asymptote for our exponential function is at y equals 0. So interchanging our x's and y's will get us these 3 new ordered pairs, 1/2, -1, 1, 0, and 2, 1. And so if we also have to switch our x's and y's for domain and range, that also applies to your asymptotes. So if you have an asymptote at y equals 0 for your exponential function, then your logarithmic function has a vertical asymptote at x equals 0. And if we look at this graphically by graphing these 3 key points, in red here you can see your 2 to the x graph, and in blue you can see your logarithmic function graph, and in purple we have the line y equals x, because reviewing and recalling from inverse functions, there is a symmetry across the line y equals x, or is a reflection. So if graphs are reflections of each other across that line of y equals x, then they are inverses of each other. So if we kind of build on these characteristics of inverse functions, we know that they are reflections across the line y equals x. We know that inverse functions interchange the x and y coordinates of the exponential function to graph the logarithmic function. We know the domain of our exponential function is -infinity to infinity, and if all our x's and y's are interchanging, then that means our range of our logarithmic function has to be -infinity to +infinity. We also know that the range of our exponential function is 0 to infinity, which means its domain of the logarithmic function has to be 0 to infinity. Another characteristic we know about exponential functions is that the y-intercept is always at 1, because anything to the 0 power is 1. So if we interchange our x's and y's, then our logarithmic parent functions will always have an x-intercept at 1. We have a horizontal asymptote for our parent exponential functions at y equals 0. And so if we interchange our asymptote of y equals 0 to x equals 0, then we have a vertical asymptote at x equals 0 for our logs. If the base is greater than 1, we talked about how that was exponential growth or an increasing function for our exponential functions. So logarithmic functions, when the base is greater than 1, is also an increasing function. It rises from left to right. And if the base is between 0 and 1, it is a decreasing function. Your graph will fall from left to right. So let's take a look at kind of our transformations here. I'm not going to spend a ton of time going over this table. You have it in your notes to refer to, and transformations is something we've been working with throughout this entire semester with every parent function we've learned. So none of the rules have changed or the order. Just the way it looks written with a logarithm is the only thing that is different. So let's take a look at an example. Log base 2 of x plus 3 plus 4. First thing you want to do is identify the parent function and the inverse parent function. So looking at the fact that it is a base 2, its parent inverse function is 2 to the x. We talked about what 2 to the x, the ordered pairs are, again, from your previous exponential lesson and from the previous few slides. So its parent its parent logarithmic function is log base 2 of x with nothing being added or subtracted to it. And so we know that if we flop the ordered pairs of 2 to the x, we will get the ordered pairs for log base 2 of x. So looking at the graph that we're trying to graph here, we want to figure out what's transformationally happening. So this plus 3 is going to actually move your graph 3 units left, and the plus 4 moves it up 4 units. So if we use our logarithmic parent function, the ordered pairs in blue here, and the way that we need to transform our logarithmic graph, we can obtain our new transformational graph. So if we take the point 1, 0 on our parent function and we move left 3 units and up 4, we are now sitting at the ordered pair -2, 4. And we can do that same thing for the ordered pair 2, 1 on our parent function. If we move left 3 and up 4, then we get the ordered pair -1, 5 on our new function. And you can do the same thing for the ordered pair 1/2, -1. So the domain we can find in 2 ways here. We can take the x plus 3, since based on the definition of a logarithmic function, what sits in here has to be greater than 0. So we can take x plus 3, set it greater than 0, and solve for x. So x has to be greater than -3, which means starting at -3, not including -3, off to infinity. We know the range of every logarithmic function is all real numbers. And if the domain is -3 to infinity, that means its vertical asymptote has to be at x equals -3. If you have a vertical asymptote at 0, a left or right movement is the only thing that's going to move that vertical asymptote. And so if we had to move left 3, our vertical asymptote is now sitting at -3. All right, let's take a look at another example. Same steps. So log base 3 of -x minus 4. So looking at the base right here, which is a subscript of a 3, then we know our inverse parent function is 3 to the x. So we go through the process of finding those key points. 3 to the -1 is a third, 3 to the 0 is 1, 3 to the first is 3. We then look at the logarithmic parent function, which is log base 3 of x. And we take our 3 to the x ordered pairs and we flip them to get the ordered pairs of log base 3 of x. We're then going to describe what transformations are happening to our function g of x, which is right 4 units and a reflection across the y-axis. Remember, a negative on the inside causes it to reflect across the y-axis. So let's go ahead and apply that. So we have the ordered pair 1, 0, and we're going to go right 4, which puts us at 5, 0, and we're going to flip that across the x-axis, so now we're at -5, 0. If we take the ordered pair 3, 1, and we go right 4 units, we will then be at, 7, 1, and if we reflect 7, 1 across the y-axis, we're now at -7, positive 1. And you can do the same thing for that ordered pair 1/3, -1, just approximating where it will fall. It'll be some decimal value. Also notice that if your horizontal asymptote for your parent function is normally at 0 and we moved right 4 units, your asymptote is now going to be sitting at negative 4. Excuse me, positive 4. And then you have to reflect across the y-axis. So if you reflect your vertical asymptote across the y-axis, you're now at negative 4. You can also solve for the domain by taking, by the definition of a logarithmic function, negative x minus 4 has to be greater than 0. So if we solve algebraically, we'll add 1, divide by a negative 1, and so x has to be less than negative 4. Remember, when you divide by a negative, that flips the direction of your inequality. And so if you're less than negative 4, the furthest left you're going is negative infinity, and the furthest right is negative 4, not including negative 4. The range I left as negative infinity to infinity because the range will always be all real numbers for your logarithmic function. And as we already discussed, when you move right 4 and flip across the y-axis, your vertical asymptote is now at x equals negative 4. So the additional example here is not in your notes, and I'm going to actually record this on a separate as a separate link because I'm running out of time on this one. So just please click the second link and you will find that you will see an additional example of how to graph a natural logarithm. I just want to do this and add this in somewhere in your notes because the natural logarithm seems tricky. It's the same process, but without the subscript, we want to talk about that. So this is an additional example I want you to add in your notes, and then once you watch that link, I'm going to have you complete some practice problems as well for homework. All right, so look to click the next link, and I look forward to seeing you guys then.